Welcome guys, myself Kiran Surendranath. I am a fall 2020 CS 6 to 60 student with Georgia Tech. Today I am going to give you a brief overview of the paper titled An Ultra Lightweight White Box Encryption Scheme for Securing Resource Constrained IoT Devices. Yes, of course, when I saw this title I thought I'm not going to make it, but when I split that into 3 or 4 parts, it was very easy. Believe me, guys, it's really interesting. We can split it into 2 or 3 parts and understand the title easily. Let me start with the last 2 words, IoT devices. So IoT, as many of you know, it stands for Internet of Things. So what does it mean? So suppose you are going for a road trip and there will be roadside sensors which record the videos, which will be detecting the speed of the vehicles. So then maybe you may be wearing some smart devices like a smart watch. So all these attribute to IoT, Internet of Things. They capture the data, they transmit the data with a securely to a server or somewhere backend, and then process it, right? So that's about IoT devices. And what do you mean by resource constrained IoT devices? So again, so if you think from the roadside sensor point of view, that sensor is sitting beside the road, right? The number of CPU or the memory available is very limited. It is not in a data center. It doesn't have the backup of a server or a PC. So we have to contain the programs or the encryption or the security, or whenever we think about those devices, we should be the resources available to us will be limited. That's what it means by resource constrained IoT devices. That I hope the last line is clear now. Now let's see the white box encryption scheme. Okay, so another characteristics. If you think where this, I'm taking the same example of roadside sensor. So if you look at that sensor, where is it located? By beside the road. So who have access to it? The public. So adversary can go snatch the device, capture the device, and go and do a reverse engineering to understand how it works, how the process works, how the encryption works, what are the things inside it, everything, right? So that's why it's called white box attack, right? So that's what we call it as a white box attack. So to handle such a scenario, we need an encryption which will think from the point of a white box attacks. So that's all about white box and encryption. Then ultra lightweight. This is very similar to the resource constraints. This is very linked to the resource constraints of an IoT device. So whenever the resource is constrained, we have to come up with an encryption which should not consume much of the resources. It should be lightweight, right? So that's all about it. This paper is proposing a lightweight encryption scheme which can be used in a white box attack context, and especially for using in a resource constrained IoT devices. That's it. So let's move to the next one. So in this slide, I have given the source of this paper. This is from the annual conference of computer security and applications conducted in December 2016. And it's a very interesting paper. So let's see. Okay, in agenda, we will start with an abstract, then goes to introduction. Then we have a section on white box cryptography, the strategies adopted in this paper, then algorithms used for encryption, decryption, and data. Then we do a cost and performance analysis and a security analysis, and then we conclude. And finally, I have given a references section. So briefly, this is all the different things we are going to discuss. Now, so you know, the abstract of the paper briefly discuss about the overview of the things we are going to discuss. Then introduction will tell the scenarios in which the solution is relevant. Then white box cryptography discuss the different algorithms and the existing algorithms, and then what is lacking there, so that we are coming up with a new suggestion. The paper is coming up with a new suggestion. And finally, the different strategies. I believe there are 7 strategies specifically the authors are mentioning in this paper. So we will go through the different strategies. Then finally, the algorithms they came up with for encryption, decryption, and data setup. There are mainly 3 crux of this whole paper is those algorithms. Then we'll get into the cost analysis. Means here we will calculate how much storage is needed, all those things. how effective this algorithm is. Then we will do a performance evaluation. We use different test beds like an Intel platform and a Raspberry Pi platform to do the performance evaluation of this algorithm. Finally, a security. So how secure this is, we'll do from how this algorithm can be attacked. So from using brute force or other methods like that in the security section. Finally, a conclusion and the reference section. That's all about today's plan. So with this, we'll move to the next section. Okay, in abstract section, we are going to get an overview of this paper. As you know, Internet of Things is no longer a fancy term. It is well integrated into our day-to-day life now. You name it, like roadside sensors to wearable devices like smartwatches. It is knowingly or unknowingly, it is a part of human life now. So whenever such a scenario comes, the complications arises as well, right? So the complications involved in securing the data and how much what we can do to secure and the trade-offs we have to do between computational cost versus security, all those things. So this paper specifically concentrates on IoT devices with limited infrastructure, that's limited resources available. So with the restricted resources, if an IoT device exists in an white box attack environment, means it is open to adversaries to capture and analyze the encryption in depth. In such a scenario, this paper put forward an algorithm through which we can encrypt with a minimal resource requirements. That's all about this paper. And finally, towards the end of this paper, we will get an idea on how secure this is, how performant this is, how efficient this is, or that is towards the conclusion of this paper. With this, let us move to the introduction section. All right. So in introduction section, so IoT interconnects smart objects and extends internet, the basics of IoT. Rapid development is happening in the IoT space, and so the security as well needs to cope up with this development. So it should be really secure, and the different schemes, right? So that is the next important topic the paper discuss. The different schemes, like three main things: black box, gray box, and white box. So black box attack context is like only functionality of the crypto system is known to the attacker, whereas gray box, some leakage functions, some information is available to the attacker, but white box, total visibility of the crypto system. For this paper scope, we are looking at white box attack context. Devices, also the devices which are deployed in an unattended manner. So unattended manner can be in public, not necessarily it needs to be in a commercial segment. That's the next bullet point. So you can have RFID readers attacks, and tampering the attacks can be classified, but it need not be in a commercial segment always. So it can be in military as well. So outdoor sensors captured by an attacker is another example. So let's see. So then comes the concept of symmetric versus asymmetric, which is better. So the paper discusses and informs us that symmetric is suitable for embedded devices because asymmetric encryption has complex computation like modular exponentiation of large integers. So some of you may be doing a course on intro to information security, where we are doing a Python program to do a modular exponentiation. And you know, when we change the function of the power function, sometimes it works, sometimes it takes longer to compute. So you might get a clue. Symmetric means we use the same key and for the encryption and for the decryption. Asymmetric is on the other way, right? It's so public encryption comes under asymmetric. But in this case, we are using an embedded device like IoT with the minimal resources. So symmetric encryption is more useful or more apt here. But the thing is, like, symmetric algorithms exist, but in a hostile environment where the attacker gets a complete visibility into the environment, the symmetric encryption schemes are not that suitable. The standard things are not suitable because the attackers can do reverse engineering, side channel analysis, probing into the chip architecture. All those things can happen. So as I mentioned, these things can happen either in commercial or in military, anywhere we use IoT devices, this can happen. Then the paper discusses about normal symmetrical encryption algorithms like AES, Advanced Encryption Services, DES, Data Encryption Services. all those things are, but unfortunately they are prone to attacks, right? So they are prone to specialized attacks as well as general attacks. So it may not be a best use case for us to use the available things. That's why in 2016 this paper is coming up with a new algorithm which is useful in the case of an IoT device with constraints. The constraints mainly on memory, whether memory is limited, processor may not be powerful, but we have to still ensure a medium level of security. So in such cases, the paper proposes this new algorithm which is ultra lightweighted. So when we reach towards the end of the paper, we will see that how much is the difference. We are the paper shows us it needs only kb, the tables and the data we need to static data we need to store is only in kbs. So it is ultra lightweighted. Then the main thing to note in this paper is it uses lm structure, the Macy structure. So this is one of the algorithm or the first algorithm as far as the authors know, which uses LM structure to do the encryption. So we'll come to that soon later, and we will be referring to Macy structure as LM structure going forward. Then strong security measures. So the authors have done theoretically tested the algorithm against different attacks, brute force and other kind of attacks. We are going to discuss that as well soon. So, but this algorithm stands very secure. With this, we will move to the next section, white box cryptography. In this section, we are discussing the existing WBC algorithms as a prerequisite or some historical information before diving deep into this paper. So any WBC algorithms, if you consider, there are two key factors. The first one is the computational cost, and the second one is level of security. Unfortunately, these two factors comes as a trade-off, means both cannot coexist or both cannot be achieved simultaneously. So again, computational cost we can again classify into two, called lightweight and heavyweight. So typically there are algorithms like the well-known block-based ciphers, DES and AES as white box versions. In the paper, we denote like WB-DES and WB-AES. They are white box implementation of classical block ciphers. So also there is the paper speaks about other algorithms which are called based on SAN structure. SAN stands for Secret Multi-Layer Substitution Affine Network. So these are the existing WBC algorithms, but they have its own different purpose. For example, if you look at WB-AES algorithm that focus on decryption. For example, if you are playing say a movie in your PC in the media player, WB-AES concentrate on the decryption side. So it's in the content presentation layer for the decryption that algorithm concentrates. So specifically, this paper is focusing on the encryption and its efficiency. So not on the decryption like WBAES or other algorithms which are out there. So this paper focus on the encryption. That's what we are going to focus. Now let's move to the next one. In this section, we are going to discuss the design strategies mentioned in the paper. So it starts with different strategies, and we are going to discuss the 7 strategies mentioned in this paper. But before that, this encryption, just to as a recap, is introduced as a low, ultra lightweight WBC algorithm, and it is introduced. It is being proposed as a because the existing algorithms lack or have some vulnerabilities, or they are not capable of handling the lightweight architecture. So keeping all that in mind, the authors are coming up with the strategies. Strategy 1, secret structure will be used. Strategy 2, LM structures will be used. I mentioned about LM structure a couple of slides back. That is a key part of this solution. Then the third one is big S boxes in at least one of the layers that will be used. And the fourth one, LM structure is modified to have more secret components. And the fifth one, 2 branches of LM structure should be protected. Sixth one, 2 layers of random and secret S boxes on both sides of the LM structure is used. And the final one, linear transformation is applied. So these are the main design strategies and points which are kept in mind while designing this new encryption algorithm. We are moving to the next one, the different algorithms. This is the core part of the solution. And in this algorithm, there are mainly three algorithms we are going to discuss. The static data generation algorithm, data gen, the encryption algorithm, ENC, the decryption algorithm, DEC. The encryption algorithm focus should be on lightweight and should run on devices with low memory, low storage, whereas the decryption algorithm assumes deployment in a secure context. It is deployed in the backend, and we can deploy that in a server or a PC, and there is no restriction. The traditional decryption algorithms, DES, AES, uses key and external encodings. And this one takes a set of static data as fixed input for matching encryption algorithm. This is the crux of the proposal. So if you look at the algorithms, so we have three algorithms mentioned: encryption, decryption, and for static data generation. So, and encryption is on focuses on the ultra lightweight side, whereas decryption assumes that the deployment is in a secure context. So moving on, so we have the algorithms now covered. Now we will look at the cost. In cost analysis section, we are going to assume that the encryption is expected to run in devices with limited memory, but only encryption, not decryption, not the point, because decryption is expected to run in servers with enough storage. So basically, the cost analysis in this paper covers or try to evaluate the cost of encryption, not decryption. There is decryption also accounted, but mainly the focus is on encryption. So that's what it is. Then there are two lookup tables used: T boxes and F boxes. So T boxes, each table is of 2 KB. So for 8 boxes, it will be 16 KB. And for F boxes, each table is 1024 bits. So for 96 tables, it will be around 12 KB. So the points you have to note is the storage requirement of the lookup tables or whatever it is in KBs, not even in MBs. So it is going to be a lightweight algorithm. And the graphs below shows the number of rounds. Number of rounds varies up to 32. It is limited at 32. And the size, that's the first graph here. So 32 rounds over here, and it is around, size is around 92 KB, 92 something KB. So that's about the size of this algorithm on the encryption side. And the next two things shows the number of operations of encryption and number of operations in decryption and the number of rounds, these two graphs. So basically the conclusion is that it's a very cost effective algorithm and a light or ultra weight encryption algorithm in the WBC context. Now we look at the performance evaluation. So performance evaluation, so we are using the platform used is, there are two development boards used: Intel Galileo Gen 2 as well as Raspberry Pi, and the graphs are shown on how the algorithm performs in both the boards. So the first one is on encryption side. On encryption side, again, the rounds are limited to 32, and it performs around 1.9 milliseconds. Whereas on the decryption side, it assumes it is going to run on a PC or a server with enough storage. So this is the graph and metrics when it runs on a separate or backend server or a PC. So again, 32 round. In this section, we are going to discuss how secure this new proposed algorithm is. So the paper discusses, initially tells about the two matrices or two aspects through which we can measure a WBC algorithm. So those are white box diversity measure and the white box ambiguity measure. So the same metrics have been used to analyze this algorithm. So we will see what is a white box diversity is. Diversity counts the number of distinct constructions which measures variability among implementations. So how much variability is there between implementation, that shows its diversity, and it is useful in foiling pre-packaged attacks. On the other hand, the ambiguity, the white box ambiguity measures, it shows the counts the number of distinct constructions that produce the same table. So one thing to note about this algorithm from the security point of view is that this is the first algorithm, as far as the knowledge of knowledge of the authors at that point of time. This is the first based on LM structure. So the other attacks which are based on block ciphers won't, this algorithm is not vulnerable to them. So this is, but there are a couple of attacks which are applicable, which against which this algorithm was tested. So the first one is how much this algorithm is resilient against attacks on secret SANs, and the second one is resilience against brute force decryption. So both these aspects are covered in the security section. And the mathematical modeling is also covered in the paper to show that how secure the algorithm is. With this, we are moving to the conclusion part. So this algorithm we have seen, it is an ultra lightweight scheme. We have found the cost impact. It is in KBs, even the tables, different rounds and different variations. We have seen the graphs. It's all within a range which we can embed in a resource constrained IoT device. So it's immune to variety of attacks. We have seen the security aspects. So it has scored good there as well. And it is the first WBC scheme to utilize the features of LM structure. This is the core and crux of this solution, I would say, because many of the attacks are not valid, which are based on the usual non-attacks based on block ciphers are not valid in this case, because this is based on LM structure, modified LM structure. We have seen the different strategies the authors adopted. So then relatively small amount of static data, we know we have seen maximum 90 kbs of data. So for the lookup table. So and the security. So we have done testing against the different WBC algorithm, and this model proves that it is indeed a secure thing, secure and then efficient. So we have done the testing of it on different test platforms, Raspberry Pi and Intel Galileo, and we have seen the graphs showing its performance. So this is an secure, efficient, and an ultra light encryption algorithm which we can use in embedded IoT devices. That's about it. The next session shows the references. I refer to the textbook of cyber physical security course for some of the topics. And then finally, that's it. Thank you for listening in. Thanks a lot. Have a good day.